Welcome to range query structures. These structures answer questions like the sum or the minimum over a range of values, and they answer them fast. Prefix sums work well when the data does not change, while a Fenwick tree, also called a binary index tree, and a segment tree handle updates too. The cost of one query drops from big O of n down to big O of log n. Let's start with why we need these structures. First, we will feel the pain of answering the same range question over and over. A range query asks for an aggregate over a range of values, such as a sum or a minimum. We start with sums. The slow way scans the range and adds every value. This chapter precomputes the answers once, then looks up just a few of them. Let's see what you will be able to do. First, you will answer a range sum query from a precomputed prefix array in big O of 1. Second, you will trace a Fenwick update path, following the I plus equals I and minus I jumps by hand. Third, you will explain a segment tree nodes interval, which range, low to high, any node covers. Fourth, you will update and query fast. Fenwick trees and segment trees both do the two in big O of log n. And fifth, you will know when lazy propagation is needed, which is for range updates, not just range queries. One idea runs through this whole chapter. Precompute summaries once, so that a query combines a few of them instead of scanning the data again. Prefix sums, Fenwick trees, and segment trees each trade simplicity for faster updates. Picture a bank statement. You look at it and you ask the same kind of question again and again. How much did I spend from March through July? That is just the sum of a range of rows. What is the net change between these two dates? Again, it is the sum of a range of rows. What is the total of rows 200 through 5000? One more time, it is the sum of a range of rows. The slow way is simple. You start at row I, you go to row j, and you add each value along the way. Let's watch this scanning hurt. One range sum query scans the whole range. That is big O of n work. Now say you run 1,000 queries on 1,000 rows. That is about 1,000,000 additions. Worse, you add the same numbers again and again, on every single query. Scanning answers just one query in big O of n from many queries on a big statement. This is far too slow. The total work grows with the range width times the number of queries. You need a better way. Prefix sums fix the slow query. You precompute the running balance once. After that, any range is one subtraction of two running totals. The range sum from I to j equals the running total at j minus the running total at I minus 1. Two lookups and one subtraction, no scanning. So the query drops to big O of 1. It is instant, no matter how wide the range. But if you fix one past transaction, every later running total changes. You must re-add the whole column, which costs big O of n for each update. Watch out here. A prefix sum works best for static or rarely updated data. Once the data changes often, that big O of n rebuild on every update becomes the new problem. Now imagine a 1,000,000 element array with 1,000,000 mixed updates and queries. The gap between the two approaches becomes clear. A prefix sum rebuilds on each update. That is big O of n, about 10 to the 6th power operations. Over 1,000,000 updates, that is about 10 to the 12th power, roughly 1,000,000,000,000 operations. A Fenwick tree or a segment tree costs big O of log n per update, about 20 operations. Over 1,000,000 updates, that is about 2 times 10 to the 7th, or 20 million operations. A Fenwick tree and a segment tree answer both the query and the update in big O of log, and you give up a little query speed for cheap updates. A trillion operations versus 20 million is the difference between never finishing and finishing instantly.